I was saying, with enthalpy, when it says processes occurring at constant pressure, fortunately for us, when we do our labs, everything's at constant pressure. What's the pressure going to be? Whatever the atmospheric pressure is at that time. Now, if we were doing a lab over the course of 3 days, that might become somewhat of an issue because the pressure can change, over the course of those 3 days. But if we're doing something for an hour or maybe 2 hours, unless a hurricane's blowing through or a tornado, our pressure is going to be relatively constant. Does that make any sense? So it makes it really nice. So this is a nice way of accounting for the flow of energy as heat without having to do a bunch of other things about that. The PV work, that piece is going to come into play really soon here. Now, you can't typically measure enthalpy as a standalone quantity like you can measure mass or temperature or volume or something like that. So what we usually have to do is look at the change in enthalpy, and there's a handy dandy equation that goes with that. It looks like this. Okay, earlier I said something about PV work, right? So here we have a gas, obviously air, inside this syringe here. If we were to somehow be able to heat up the air inside of that syringe, what do you think might happen to the plunger? It would probably go up, okay? So would the volume of the air change, of the gas change? Absolutely, okay? So do you guys remember what work is? Force applied through a distance, okay? So will a force be applied to that plunger? Yes. Will it move a distance? Yes. So the volume would increase. Therefore, that would be pressure volume work. See where I'm going with that? So when it was referring to other than PV work, that's what it was referring to. All right, so anyway. So now we've got this, the delta E is the internal energy. We're going to get into more about what the internal energy means, but it has things to do with the molecules and the atoms themselves. And let's say we're talking about molecules, the actual amount of energy, temperature, heat of that those molecules have. And then the work, obviously, is the PV part. You can see, I think I've got a couple arrows doing that, right? All right, so now we're going to derive a couple of equations and show why delta H or enthalpy is a valid function at constant pressure. Okay, internal energy, I put another little oval down there, right? That is equivalent to Q plus W. Okay. Now, Q, you might remember from your calorimetry stuff that we did, is energy is heat. Okay. That's already on your thing, and we can calculate Q. Does anyone, I already mentioned the equation, Q equals MC delta T. So we can actually measure Q fairly easily. One of the methods that we used with the metal lab, like I described earlier, is we heated up the metal in a water bath, put the metal in a lot of cool water, which we already knew the temperature of. We accounted for the temperature change of both of those pieces. We assumed that the amount of energy that the metal lost to the cool water was gained by the cool water and nothing else. Okay, and that was the tricky part of that lab, was getting that metal into that cool water as quickly as possible so the energy didn't go elsewhere. But anyway, by knowing the heat capacity of water, which we'll go over here in a little bit, and the temperature change of the water and the mass of the water, we can find out how much energy that the water gained. We assumed that the water gained that energy from the metal, so therefore we knew the amount of metal or heat that the metal had lost. We knew the mass of the metal, we knew the temperature change of the metal, therefore we could find the metal's heat capacity. Okay, it's a fairly simple process. M is mass, T is temperature, Q is, C is a specific heat capacity. Okay, over on the other side with the work piece, if you remember, as it says there, work is a force applied through a distance. Well, in the case of that syringe, remember distance is any length, okay, whether it's vertically, horizontally, or some sort of something in between there. So I just substituted the D with an H for height, okay? And we already know, I think, that pressure is force divided by area, okay? Which we can rearrange that to solve for force, and force equals pressure times area, okay? With all of those things being true, force times height is work, and force equals pressure times area, we can derive this equation. QE okay, we can derive that equation. Now, thinking this through, area is length times width, times height is volume. So work equals pressure times change in volume, which I've already shown you. Just showing you where this stuff comes from. However, what that's going to do, where'd my syringe go? What is the system we're considering in this case? It's the air, the gas inside the syringe, right? We had talked about heating that, okay? In which case, what happened to, well, let me reverse this. Let me do this. What if I applied a pressure to the syringe? What happened to the gas inside there? What happened to its volume? It decreased, okay? So change in, we had a final volume that was smaller than the initial volume, right? So we would have a negative volume change if you look at it that way, okay? However, since the gas is the system, work was done to the system. Would you agree? Okay. Well, in that case, that would be an endothermic process. We would like that to be a positive value. But we just got done saying that the change in volume would have been negative. Where I'm going with this is, just like in many cases in chemistry, we have to rewrite this equation as W equals negative P delta V, because that negative sign turns everything over to the system's perspective rather than the surroundings perspective. So, where I'm going with this is, currently these are the two main equations that we need. Because now look at what we have. Earlier we said delta H equals delta E plus PV. We already talked about what delta E equals. Sorry I didn't put that up there. My bad on that. Now we know where to get the Q from. Now we know where to get the W from. Okay? So when it's all said and done, by substituting some things in there, I essentially get this. that's what it comes down to. And since positive work plus negative work cancels out, essentially 0, what we get is delta H equals Q, and that's where the at constant pressure thing comes into play. So this is kind of the last thing that we need to look at currently. Now, delta H is a state function. That's possibly the first time we've run into this. Does that phrase come up in anything that you guys have talked about before? All right. It's a pretty simple concept. You just haven't thought about it yet. A state function is one in which it doesn't matter what pathway it takes to get there, the quantity's still going to be the same. We've got a couple analogies that I like to use for that. That's pretty steep. All right, so if we have a ball that's a certain height above like a flat spot here, all right? And let's go into the physics world and talk about a frictionless surface with no air resistance. You know, that magical world in physics where it's a frictionless surface, and so usually I get a lot of chuckles there, because don't you guys do that all the time in physics? Talk about the frictionless surface and no air resistance? Okay. Well, let's say this ball starts rolling down the hill, okay? What type of energy does it currently have in its current position? Gravitational potential energy, that's it. What's its total energy? Whatever the gravitational potential energy is, because there's no other source of energy, right? Now, what if the ball were to, let's say, you know, something was holding it there, it was wanting to move, but it couldn't because something's holding it there, and we removed whatever it is that's holding it there. Now what's it going to do? Again, frictionless surface, no air resistance. Well, it's going to roll down the hill. And when is it going to stop? Never. Once again, frictionless surface, no air resistance, there's nothing to slow it down, it's going to roll forever. What is its current, so what is its total energy as it's moving forever and ever and ever? Well, it's now all kinetic energy, but its total energy is whatever it had been before, okay? Now, let's imagine another scenario. So work was done, right? We had a force, gravity, being applied to this object. It moved a distance, okay? Now let's change things up a little bit. All right, so what did I just introduce? I just introduced friction, right? So now, once again, same height, same ball, same mass, all that good stuff, has the same amount of energy as it did the first scenario, exactly the same amount. But now, as it rolls down the ramp, what's going to happen? At some point in time, because of the friction, it's probably going to, it's going to lose its gravitational potential energy, it's going to increase its kinetic energy, but some of that energy is going to end up being lost as heat, one way or the other. Would you agree? Okay? So therefore, its total energy that it had the ball lost the energy, but the total energy that was in the system stays the same. Some of it got lost as heat, though. And that's what we mean by a state function. Doesn't matter how the ball got here, the total energy that was involved in the system stays the same. It just went different ways. Some of it went through, where's my equation? Here we go. Some of it went through work, change in position. Others of it got lost as heat. In one case, this was 0. In other cases, it wasn't. In the second case, it wasn't 0. Total energy stays the same. That's what we mean by a state function. That'll come in into play a little bit later. All right, there's the theory behind the whole enthalpy thing. Now we're actually going to start using that stuff. So if you turn over to the next page. We are going to come up with 3 different ways of calculating enthalpies in a chemical process. The first way will be in these first pages or 2 here. Enthalpies of reaction, otherwise known as delta H's subreaction. We call those sometimes heats of reaction. We're going to learn to write thermochemical equations, which is exactly the same as an electrochemical equation, except of having an E cell, now we're going to have a delta H. Exactly the same idea. So, couple examples. Hey, it's supposed to be pretty nice tomorrow, isn't it? Temperature-wise? You might be wondering why I said that. Thought that was a relatively random thing, didn't you? Sorry about that, I didn't leave myself enough room. That equation that I just wrote down, that you guys are currently writing down, I think that would be a good reaction to actually watch happen tomorrow. I think we'll do that reaction tomorrow. That might be kind of fun. Oh, look at that. I am all set for it. Forgot about that. That's cool. Anyway. That was a weird place to put a 3. I don't know why I did that. Iron 3 oxide plus aluminum. All you need is a little energy to get that baby started, little catalyst. Anybody know this reaction at all? Oh, there will be fire. There will be more fire than you want. You guys ever heard of thermite?
Oh, yeah,
Yeah, I think we'll do this tomorrow. Okay. I'll have more stories about that tomorrow when I'm not videotaping, but currently I'm not going to tell those stories. Anyway, there's one. Now, like I was saying earlier, just like the E cells, okay, when we have the entire reaction, we have an enthalpy that's associated with it. What types of information is that enthalpy providing us? Well, it has a negative sign, which tells us that it is, well, here's specifically what it tells us. That means these reactants have X amount of energy. These products have X amount of energy. Except these products, relative to the reactants, have less energy by this amount. Is that making any sense? So this is an exothermic process. Remember, the negative sign tells us that it's exothermic. So the reactant, Fe2O3, has a certain amount of energy. The aluminum has a certain amount of energy by itself. When the interaction between these two things occurs, bonds are broken between the iron and the oxygen. Bonds are formed between the aluminum and the oxygen. I'm getting ahead of the game here a little bit, but I thought, the more times you hear this, the more it gets drilled in your brains. And my kids at the end of the year, last year, got really good at understanding this. Is breaking a bond an endothermic or exothermic process. So you're saying energy is given off when bonds are broken. Are you guessing?
No, I know.
You know this.
I'm pretty sure I know.
Turns out he doesn't know. To break a chemical bond is always an endothermic process. Remember, the things are bound together because they're at a lower energy state than if they're apart. So breaking any type of chemical bond, covalent, ionic, polar covalent. You guys learned about polar covalence at one point in time or not? We will this year if you did not, okay? Breaking any kind of chemical bond is always an endothermic process. It requires energy to take things apart. Forming chemical bonds is always an exothermic process. Always, always, always. You're going to hear this like 18 times this year. You're going to get really sick of me saying it. I hope you do. Because if you get really sick of me saying it, that means you know it. All right? So that means these two things separately have higher energy than these two things separately. And that energy had to go somewhere. It goes out to the environment as heat and or work. If we had this contained in a particular area, pressure volume work would be performed, okay? If we had done the experiment in this, pressure volume work would have been done. This would have melted also, but still, regardless. Okay? You'll find that out tomorrow. Moving on, another example. Actually, I can do both of these. Anyone want to take a stab? Yeah, please do that. Oh, there's something I forgot. Should have known this one. There's a weird phrase that you're going to run into here in this book, and it's not going to make a lot of sense. When I say per mole, you would say negative 878 kilojoules per mole of reaction. For the water one, you'd say negative 483.6 kilojoules per mole of reaction. For whatever it means. Okay. Now, a couple of key points, 3 key points that I want to talk about, and this is a couple of these are the difference between this and the electrochemistry stuff that we're working with. First key point, delta H is an extensive property. And we talked about that last week, I think, when we were talking about reduction potentials. Remember, reduction potentials are intensive properties. Doesn't matter how much material, how many times the process happened, it's still the same value. Delta H is an extensive property. The amount of material must be accounted for. So there's some stoichiometry involved in this. Delta H's of reaction, delta H reactions are equal in magnitude, but opposite in sign to the reverse of the delta H reaction. Okay, so put it this way. Let me put that in other words. If I reverse this reaction, what would the delta H be? Positive 878 kilojoules per mole. Okay? Similar to, that piece is similar to the E cells, or the reduction potentials. If we reverse the reduction potential, make it an oxidation, the sign on the reduction potential changed. And lastly, the heat of reaction, delta H reaction, sorry about that, delta H reactions depend on the state of matter of the reactants in the products. For example, if we had some, let's say this, if we had some molten Fe2O3 instead of solid Fe2O3, think that through. If we had liquid Fe2O3, how would we get that to be a liquid? We would have to add energy to it. So it's already got a head start. Does that make any sense? All right, so where I'm going with this is, in the back of your book, we're not there yet, but in the back of your book are a bunch of delta H's for a bunch of substances, okay? Depends on the state of matter. This is for gaseous water. Liquid waters is going to be different. To form liquid water is going to be a different value. That's all I'm saying on that one. All right, moving on. We can quantitatively see this by looking at the following example. We can take some hydrogen peroxide, decompose it to water and oxygen by the following reaction. I think I already wrote the reaction, didn't I? And I gave you the delta H. So that is an exothermic process. As it turns out, many, I'm not going to say all by any means, I might even almost go to most chemical processes are exothermic processes, although that's not always the case. Anybody think of an endothermic process? Well, does anybody do anything athletically? Sports of anything? Do you run? Try not to run. JAMA, gymnastics counts. Okay. Do you ever, oh, sorry about that. I was gonna ask if you ever sweat, but you're a girl, so do you ever perspire?
No.
No? Okay. What happens when you sweat? Or glisten for you young ladies? Glisten, you guys glisten. Why do you guys sweat? What's the point of that? You don't even know. What's that? The whole point is to cool off. But how is that cooling you off? And how is the water on your skin evaporating?
It requires energy to evaporate.
You're adding energy to the water to get it to become a gas. That's an endothermic process. I'm just saying, that's an endothermic process. Has anyone ever used a cold pack before? For like an injury or some sort of thing, right? You get this little plastic baggy kind of thing, probably got some liquid in there, it's got something else in there, you kind of have to hit it or something like that or smash it together. Do you guys know what's in those things? Most of the time it's sodium thiosulfate. Anybody developed film before? Some of you have. Black and white film. That's the stuff they call the fixer. So the tray that has a fixer in it, that's sodium thiosulfate. Anyway, when you dissolve that in water, that's an endothermic process. It gets pretty cold, doesn't it? Those cold packs, they get pretty cold. It's all over in Homan's room right now, so I'm not going to run over and get it. Yeah, hang on. When you guys did your first lab, the moles of reactants lab, this was one of the unknowns. Does anyone remember the Na2S2O3? I can't remember which unknown it was, whether it was A, B, or C, but it was one of them. Okay, you guys already used this stuff.
He's a hot plate.
The stir plate, the hot stir plate. That's work. Okay, anyone want to take a stab as to what temperature the sodium thiosulfate currently is? Room temperature? Been in Homan's room? Here. Check out. And what about the flask? What do you think? About the same as everything else in the room, right? Excellent. Room temperature water? You know why it's room temperature water? Because it's in the room. Sitting in pipes that have been in the room. Good question. Kind of like the hot plate back there. You know I can just first. She's like staring at it, like, what am I supposed to do? Drink it?
I thought you were gonna smash me. Ice cold drink.
So have I gotten to you yet? Yes? Okay. You did it the right way. This side of your hand's a lot more sensitive sometimes than, you know. Alright, moving on.
Wait, it's more sensitive?
Can be.
Then why do you put that part to a fire door?
Yeah.
What?
Like, when they told us, like, if you're in a fire, to make sure the door's not hot, you put the vacuum into the door.
That's what I just said.
Yeah, but why would you want to put the more sensitive part if it's hot?
To
Is it
find out if
important?
it's hot or not. You
Well,
want to
I'm
know.
pretty sure this will be able to tell you if it's really hot or not.
See, but again, thank you for saying that. You just verified what I just got done saying.
Then it's just gonna burn more. Why would I want it to burn
But
more?
you don't touch it. You put it near it. Yeah.
Oh, I guess that makes sense.
Okay. No, I mean, thank you for saying
No,
that.
but they literally said
I know
put it
that.
on the door, and they didn't say slowly put it. They just said put it on the door.
When I have my regular chemistry kids, because you guys don't ever really get to this scenario, we're weighing things that you had heated, okay? But with my regular chemistry kids, as you know, if you had me, I yelled at you if you put something hot onto the balance because you guys, and I'm really upset with some of you, by the way, because you didn't follow those directions, and this is what you guys are doing to these.
What is it?
You're melting them. So if you had Homan in here, I blame some of you for that, but let's not go into that any further. Moving on. So anyway, there's the delta H for the hydrogen peroxide. Let's calculate the value of delta H. Now it says QP, but from now on we're assuming that enthalpies are at constant pressure. When 5.00 grams of hydrogen peroxide decomposes at constant pressure. This is not hard. It's not intended to be hard, but I'm showing you that you can do this. Remember, we just got done saying that delta H's are extensive properties. So what we would do is take the 5.00 grams, the hydrogen peroxide, convert that to moles. And then, now here's, like I said, is where the stoichiometry and the fact that it's an extensive property comes into play. Oh, the equation's not written up here, sorry about that. It's 2 H2O2 yielding 2 waters plus O2. Correct? Okay, that means this reaction and the associated delta H, was it 196? Okay, negative 196 kilojoules per mole. Well, there's actually 2 moles here. So we would use that. It was 196 point something? No? Okay. For every 2 moles of the hydrogen peroxide, because that's the substance that we were looking at. I just wanted to this is not hard, I just wanted to point this out because this is a place sometimes that students will make a mistake on that. Ends up being negative 14.4 kilojoules. Okay, so slightly exothermic when we decompose 5 grams of H2O2. Well, 1, time's about over. 2, I was going to stop there anyway because the next part goes into a slightly different thing. So, we'll stop there. We will have the opportunity to get through the next couple of pieces, but usually at this point I say bring a jacket tomorrow.